give me a hand cue with here. Hello everyone, I'm Carl with Lunchbox Sessions, CD Industrial Group, wishing a good evening to our friends from Thrivini Earth Movers in India. Welcome to our participants from Brazil, from the United Kingdom, and from Tanzania. Today's topic is closed-loop hydraulics, sometimes known as hydrostatic systems, riding lawnmowers, skid steer loaders, mining blast hole drills, coiled tubing injectors in the oil field, if you know those machines, the swing circuit on some models of mining shovels and construction cranes, the apron feeder in a mining mill. Let's see, what else is hydrostatic drives? Oh, it's a long list. Pulp mill reclaims, pulp mill washers, pulp washers, ship loading conveyors, even extruders for breakfast cereals. Maybe you know a breakfast cereal with little pieces shaped like toroids that have some fruit flavors, if you know what I mean. Yeah, hydrostatic drives in use in an awful lot of places. Let's have a look at one right here on Lunchbox. Studying of a very complex hydrostatic drive. So that's one example. See today is that we've set a number of our simulations in the hydrostatic session live so that you can play along. So even if you don't have a paid subscription. Okay. Okay, we had a little bit of trouble with audio. Not sure what you will have missed, but we're back with our audio live. I was just going through the process of listing some typical hydrostatic drives, some closed-loop hydraulic systems, and demoing one that we use for training on some very complex hydrostatic drive systems. Log into your YouTube account or your Gmail services so that you can play along with us and join us in the live chat, ask questions. You'll find out that we've got a number of our simulations on Lunchbox Sessions set free for the duration today so that you can join along and interact, use some of the exact same simulations that I'll be using during this simulation. Great to see our friends from the Yucatan and Mexico have joined us. We've got folks with Raji Steel from the Kingdom of Saudi Arabia. Thanks for joining us this morning. Participants from Peru, from India, from Egypt, from Oman, our good friends at Thrivini Earth Movers in India, participants from Brazil and UK and Tanzania. Thanks for joining us. This is our first episode of our second season, I guess, is what we would say, our first YouTube Live of the summer. And we'll have another one right away on July 22, where we'll be checking and counterbalancing because the topic will be motion control valves. So mark your calendar and join us for that one. That's on July 22nd for our second YouTube Live of this particular season. Feel free also to email us after the YouTube Live if you've got questions we didn't answer, or if you've got questions about what we do at Lunchbox Sessions and CD Industrial Group. A great email address to send that information, send your email to, is info@lunchboxsessions.com. Hey, a shout out to our friends at Fluid Power World. Fluid Power World is your resource and publication for components and for design and engineering knowledge. The Fluid Power Technology Conference continues in virtual mode with some great events. So check out the events tab on fluidpowerworld.com. All right, welcome participants from Sweden. All right, we like to start off by having a look at some photographs of hydrostatic drives from our common travels, and some of these may look a little unusual to you. If you're used to seeing a hydrostatic drive on a skid steer loader, on a riding mower, on a small piece of equipment, some of the hydrostatic drives that we end up interacting with are on an enormous scale, many hundreds of horsepower, so perhaps it won't look exactly like some of the ones you're used to, but whether the hydrostatic drive is 500 horsepower, 900 horsepower, 20 horsepower, we find that many hydrostatic drives are built, designed, and configured, and even maintained in a similar way. And so here's an example. This is an example from a pulp mill for a very large machine called a pulp washer. We saw the pump, then the motor that the hydrostatic drive pump is turning. You'll see here a bank of pressure gauges with the very typical readings that you see. Now, whether or not that comes through very clearly on your end, what you'll notice on the right-hand gauge, port A pressure is at about 2,000 psi, so it gives us a clue as to which way the hydrostatic drive is turning right now. That's our working pressure port. And then return oil's coming back on the port B pressure gauge on the left side. And for those of you who know your hydrostatic drives well, you'll know that that very minimal pressure on that left side gauge for port B is not sitting at 0. That is sitting at about, what number would you pick? Yeah, that return side pressure is sitting there at 300 psi, which is coincidentally also the same as the pressure value that you could see quite clearly in that second gauge from the left, the charge pressure gauge, and those two pressures match. Charge pressure and the return side of our hydrostatic loop are at the same pressure. Hey, also a gauge for servo pressure, and we're going to get into that topic of how that swash plate is servoed into position in the big pumps, and that servo pressure is right up there, close to 40 bar, approaching 600 psi. Some very typical numbers to run into, typical values and important aspects of a hydrostatic closed loop drive. Here's some photographs, the upper layer of pumps in white or beige color being used to power the swing drive on that example I was showing you in live schematic form just a few moments ago. So some hydrostatic drives have a very large scale. Here's a photograph of one of 6 swing motors for that model of shovel, where swinging the upper works of that shovel is a closed loop hydrostatic drive. And maybe you're even seeing some photographs here of a very large installation, but a very large hydrostatic drive, 400 horsepower, but it's perhaps making some very small pieces of breakfast cereal extruder. Here's a schematic for it. So a lot of hydrostatic drives share a lot of elements in common, whether it's a very small 20 horsepower system or 400 horsepower or perhaps more. All right, and so far I've been speaking to you about hydrostatic drives where the pump is always turning a hydraulic motor. You can see one here in our studio. We've got a hydraulic pump on a unit, and over here we've got a hydraulic motor that we're going to turn with the hydrostatic drive. But here is my pop quiz question for the day, and we'll save the answer right to the very end. Perhaps some of you will know the answer, and we'll have some systems to tell us about in the chat column. But here's my question. Is a closed loop hydrostatic drive always about a hydraulic motor, or can closed loop hydrostatic drives work with cylinders as well? That'll be our pop quiz question, and we'll save the answer to that to the very end of our live broadcast. All right, welcome additional participants from Texas and from Ghana and Africa. Glad you could join us today. All right, let's not get too far ahead of ourselves. I'm making some assumptions as you read schematic symbols and schematic diagrams, but perhaps it's a good time for us to go back to something fairly basic and think about a cylinder barrel that spins as fast as the prime mover, which could be a diesel engine, could be electric motor, and generally speaking, that cylinder barrel has 9 pistons loaded into it. Sometimes the count is 7 pistons. These are some very common scenarios. But just to remind us of what actually moves the fluid and how that change in flow direction for that very smooth forward and reverse action that you get in a skid steer loader, if you've operated one of those, inside the heart of the pump, just so that we remember the mechanical reality that we're working with, that cylinder barrel, and its 9 pistons. Here we are at mid-flow rate, full flow forward, back to center. Let's stop there for a moment. Pump at neutral. We're going to be talking a little bit about how much care does it take to keep a hydrostatic pump sitting in its neutral position so that when the operator does not call for any flow, if the operator is running a skid steer loader perhaps, lets go of the sticks which return to the center position and wants none of the wheels to be turning, how important is it for that swash plate to sit at that perfectly zero angle? And of course, the cylinder barrel is still turning. That hasn't changed. If your engine, the electric motor, is still running, the pump is still spinning internally, but when the swash plate is at that perfect zero angle, then the pistons are no longer stroking back and forth from bottom dead center to top dead center. Let's carry on and see our pump come back on stroke to produce low flow in the reverse direction. Look at those 2 kidney-shaped porting plates on the outlet of the cylinder barrel, on the outlet of the porting plate, to see that our flow arrows have reversed. Mid-flow in the reverse direction, full flow in the reverse direction. Our skid steer is going backwards about as fast as possible. Here's one look at that exact clip again. If I stopped it too many times, playing through, this time I'll let it play through and be nice and smooth. Hey, we've got some additional participants from Tunisia. I think I know who that is. Oh yeah, Sammy has joined us. Mr. Sammy, welcome. Welcome participants, also additional participants from India. Good evening to you on that side of the world. It's later in the day. Glad you could join us. All right, and Pradeep has already said that he thinks that perhaps hydrostatic drives can work with cylinders. Well, we'll see. Is it possible to do that? All right, great. So in today's session, we'll be speaking about perhaps some adjustments and some critical pressure values, and just wanted to take the time to remind you that in our short hour and a bit, this won't be enough time to teach all of the aspects and skills and expertise needed to make these adjustments safely, correctly, without damage, without injury. If you're still new to your study of hydraulics, please get some help from a master technician, someone who's done that kind of work a good number of times. The first time you go to make some of these adjustments, work with someone who knows exactly how they're done. Also, we'll probably mention some specific models, some popular models of hydrostatic pumps that we come across out there as we do our work with heavy industry. And while we may reference some features or adjustments, please note that we won't have enough time in this session to help you know all of the ins and outs of making those adjustments safely, correctly, without damage. Definitely work with the manufacturers of your hydrostatic pumps, or work with the manufacturer of the machine or the system integrator, whoever built your hydraulic system, to make sure you get the right assistance and help with any maintenance issues or adjustments that need to be taken into account. All right, let's jump into lunchbox sessions here now. And we're going to run a standard hydrostatic drive, a fairly basic, straightforward hydrostatic drive training model. Actually, what we'll do here is we'll just have a look first at a system that you have access to. Here, I'll show you where it is in lunchbox sessions if you've decided to play along. If you've got a demo account set up, that's all you're going to need to interact with us in this material. And so I'm just going to back out. If you are in our hydraulics menu, that's very easy to find. And then down low, just to the left of the middle, jump into hydrostatic drives there. And then when you scroll down past the lesson and the videos, you see our simulations. And the one I'm going to show you first is the one that is here, called Hydrostatic Training Circuit. Later on during this YouTube Live, that's the system that will be running live here in the shop. You'll probably also notice on our YouTube Live there's some links there to some documents, perhaps they're on our website as well now, to the actual model of hydrostatic pump and the motor that we chose just for our demo here today. But you get to run it. You can run this system yourself by grabbing a hold of that slider on the right-hand side there. You can add some resistance. Whenever you see a slider on our simulations that says load or resistance, that just means you're making it tough for that hydraulic motor to turn. You're making it develop some torque and turn a load that could be difficult. A winch perhaps, a conveyor, a crawler machine that has to propel up a steep slope perhaps. So that just introduces pressure from the working end of the system, from the motor. And so that is a hydrostatic drive that we run right here in the shop, and we'll make a little bit of adjustments on it with you later on. All right, hydrostatic drives. Yeah, they all have in common the ability to move that controller back to center. And if you're watching that swash plate over on the left-hand side of the simulation, close to a servo piston that is yellow and blue in color, that's moving our swash plate into position now over to about the 1 o'clock position. You'll see that our flow has reversed, and now flow is exiting from the 12 o'clock position, let's say, on the pump symbol, and our hydraulic motor is turning in the opposite position. You will also see the hot oil shuttle hard at work there, where you see a red pilot head pushing on what appears to be a directional valve. You'll see some flashing on and off on the solenoid that is piloting our servo piston into position to set our swash plate angle for the flow rate that we want. That flashing red, when you see it, is a simple depiction in our live schematics of pulse width modulation. So the further I move the controller to the left, the more current I am applying to that pilot valve, that pilot pressure valve in the upper left. More on piloting. I'm jumping ahead, but it spends more time red and less time white as we move that controller to full, and that is meant to remind you of the functioning of pulse width modulation. Mostly on, only a little bit off, and of course the frequency doesn't change. Sliding that controller back towards the neutral position, and you'll see in that same flashing solenoid, more time spent white and less time spent red. Okay, so a number of very typical features for a hydrostatic drive, and we'll come back to that one and do some more work with it shortly. All right, someone has already asked, Salim has asked, I'd like to know the pressure setting of an A4VG on a concrete pump. Well, I guess that depends, Salim. I would encourage you to look on the Bosch Rexroth site and look for the technical document on their site. Excellent resources available. and look for the technical documents for the exact series of pumps. That'll be after a slash in the model code. Check and see what size, what features you've got, and download that document. And they've got some great documentation available at Bosch Rexroth, the makers of that A4VG pump that you mentioned, and lots of good materials to help you out with that. But if you hang on a little bit, later on during this live, we will make some, we'll have a look at some very general aspects of the Rexroth A4VG. Yeah, so do hang on to that thought, and we'll come back to it and think about that briefly. You bet. Good question. Good to get the pressure set right, and there generally are on an A4VG 2, even 3 very critical pressures that need to be set in the right order. I can't say that during this YouTube Live that we'll give you a definitive process for that, but we'll look at the pressure values in general. Absolutely. Hey, great. Welcome. Some additional guests have joined us from Oklahoma and from Nigeria. Welcome to our YouTube Live. Alrighty, just let me find my place here. Yeah, so there's a lot going on in this standard hydrostatic drive for the teaching that we do here in our shop. Let's switch over now to another one that we've got. So if we go back to session here, and you're playing along, you'll find out that you can also run one of our simulations by the name of ClosedLoop with hydrostatic and brackets right there. The very first one on our list of simulations. And jump in on that one, and I guess really this is probably one of the most popular schematics out there. In a way, it's everybody's hydrostatic drive and nobody's hydrostatic drive. It's very generic, and it's useful just to get some very basic teaching done. So let's have a look at some of the basic features on this one, which is graphically about as simple as we can depict it. So let's move our slider here. If you're playing along, feel free to do the exact same thing with your simulation as I'm doing with mine. I'm going to move my slider for direction and flow. I'm going to move it to the 50% forward position. And that gets our swash plate moved over to about the 1 o'clock position. We're displacing perhaps at a half flow rate. And now let's move our load resistance perhaps to about half value, just so that we have some pressure. Again, that load resistance, that's all about making the hydraulic motor work hard, some counter torque, so that it has some work to do. It builds up some pressure in the system. And what you see now, of course, is a darker orange colored line from the pump at the 12 o'clock position to the motor also at 12 o'clock position, flow leaving the motor at 6 o'clock, and it's headed right back to the pump on the left hand side at the 6 o'clock position. So we've got a basic loop of hydraulic flow taking place. And of course, one of the things that I think comes to mind for a person who's only working with open loop hydraulics is, isn't that suction hose, isn't that return line right into the main pump, isn't that hydraulic hose just a little too long and a little bit too small in diameter? And I think if this was an open loop hydraulic system, the answer would be yes. That is a very skinny and long hose returning from the motor to feed the pump. As most of you know, if you have some experience with hydraulics, with open loop hydraulic systems, typically the inlet from the tank to the pump is the fattest diameter hose, and it's not very long either. It's a pretty short distance generally from the tank where the hydraulic oil is to the inlet of the pump. But that's for open loop hydraulics. So how do we prevent the terrible effects of cavitation, where the pump has a tough time drawing in a consistent supply of liquid hydraulic oil? Well, yeah, the hose is long and skinny, and I think you guys know the answer. Feel free to throw it out into the chat if you like. What extra device do we have to have in a hydrostatic drive to prevent the main pumping rotating group from suffering the ill effect of cavitation? Hey, I think Adam France has a question there, and he's mentioning the item in question. He's asking a question about charge pumps. Adam says, my question is, why do some pumps like Eaton have a charge pressure that is set at 15B at any input speed, diesel driven? Others like Rexroth, the pump, the charge pressure varies with input speed. Yeah, I mean, that's kind of an interesting question in a way, Adam. If you're familiar with relief valves that have only one spring and one poppet in them, sometimes referred to as a direct acting relief valve, one poppet and one spring, what you find out is that when those types of relief valves begin to crack open and allow the first amounts of flow, that turns out to be a very different pressure than when a lot more flow is being pushed through that relief valve and the poppet and spring are compressed further back. So a manufacturer may, from different manufacturers, they may have different procedures to make sure that you have set for a pressure using the right amount of flow from that charge pump. And keep in mind, the charge pump is always fixed displacement. I haven't seen a charge pump yet that is variable displacement, but now that you've gone and mentioned the RPMs, that is the one way, right, to change the displacement of a fixed displacement pump. And so the manufacturer will have its own procedure just to make sure that you've got it set right for how they've built that particular pump. Okay. Hey, Jeff Magnola from Vancouver has chimed in there, and he's throwing out a rule of thumb for the hot oil shuttle relief setting. Yes, this one's going to be important, and we're going to come back to this. There's some very important aspects for us to look at, but Jeff is saying that in his experience, the rule of thumb for a hot oil shuttle is that the relief valve, hot oil shuttle relief setting. Oh, we haven't caught up to the hot oil yet. Okay, we'll get there. The hot oil shuttle relief setting to be 40 psi below the charge pump setting. Yeah, so that's going to be a really interesting discussion. We'll have to do some thinking about that one as we move along here. But yeah, thanks for participating on that one, Jeff. The charge pump has its own relief valve, and then if there's a hot oil shuttle valve present, and by the way, it's not always there now. You'll find some mobile machinery. Oh, I can't think of a number of hydrostatic systems I've come across recently that are finely tuned and very carefully engineered and meant for continuous run, and yet no hot oil shuttle. So I would say in my experience, perhaps 9 out of 10 or 19 out of 20 hydrostatic drives still have the hot oil shuttle, but it's not always there now. So we'll come back to that one. Yeah, thanks, Jeff. Great thoughts. Okay, I'm just going to carry on a little bit with our standard hydrostatic drive and think about some of the features that are present. So yeah, that charge pump, that second circle there next to the main hydrostatic pump circle where those pistons are, and on some schematics, and it helps us to remember this, on some schematics you find out that the charge pump circle is drawn smaller in diameter than the main hydrostatic drive piston pump assembly, the rotating group, and quite often that circle is drawn smaller to remind us that the charge pump does not displace anywhere near as much in total flow as the main rotating group, the piston pump component. It's generally quite a bit smaller. And so the charge pump is there. We were talking about that long skinny hose going from 6 o'clock on the motor all the way back to 6 o'clock on the pump. Too long and far too skinny a hose for an open loop hydraulic system or for any pump to survive, if not for the fact that the charge pump, one of the jobs of the charge pump is to ram charge that inlet line for the pump. Make sure it stays pressurized so that there's no risk of cavitation to the inlet side of our hydrostatic pump. So what you'll see there right now, if you're following the yellow line leaving to the right shortly after the top of the charge pump, is that charge pump fluid is entering on the return side of the hydrostatic loop. And so if we move down the B side of the loop and find a gauge, aha, there it is. proof that our return side pressure is not at zero or some negative pressure, which would be a disaster. Good reason to keep an eye on those pressure gauges that we were showing in our photographs at the very beginning of the session. That 260 psi gauge is a clear indication that we're working with a functioning charge pump. But I think Jeff was looking at the various pressure settings and noticing that the pressure on that return line, quite correctly, is not at the pressure of the charge pump relief. It's actually at the pressure that is slightly less than the charge pump relief valve. It's at a lower pressure, 260. Okay, a little bit more on that in a moment. So the charge pump is there to help supercharge the inlet of our main rotating group so we don't have any issues with cavitation for our main pump. Hey, let's go back up to that load resistance slider and let's think about pressure control for a moment. And let's keep sliding that load resistance slider until we're giving that motor just too much work to do. We're going to exceed the torque capability of the system here and hit a pressure that is worth watching out for. Perhaps if this was a mobile piece of equipment, let's say it's a small piece of construction equipment and someone was in Propel and has now parked it up against, has hit some large obstruction, perhaps a rock wall, maybe a large tree, and it won't move out of the way. And so now we've hit a pressure that is worth calling the ceiling of the system. It's the maximum safe system pressure. And we'll say it's 3,000 psi for our system. We need to make sure that we don't exceed that value, which could cause some damage to the machine, perhaps blow off a hydraulic hose, perhaps a pump or a motor shaft would get damaged. So the machine maker, say, has set our maximum pressure to 3,000 psi. And what device has us protected? There is a cross-port relief valve there on the top branch about halfway down. And the setting of that relief valve, that's the symbol for a relief valve. Pilot pressure has come around on that dashed line. If we're thinking about it purely as a symbol, pushed our poppet open against the setting of a spring that wants to push it closed again, just like you see the closed cross-port relief on the bottom return line. But in our open cross-port relief, pressure is being limited to 3,000 psi, and pump flow is being directed back to the inlet side of the pump. Now, what do we figure is going to happen if we leave this machine parked up against the immobile object that won't move out of the way, and we leave the pump in drive? What's likely to happen? That's absolutely right. We're going to have some overheating issues. They're going to come pretty quick. So this type of system that just has cross-port reliefs, it's designed with the thinking that you will notice that you've bumped into an object that won't move out of the way, and very shortly after, you will move the machine away from that resistance and allow normal flow to resume. Cross-port reliefs can get the job done, but there's going to be overheating, okay? All right, let me just check my list to make sure I'm following all the notes I had in mind. So that's a little bit on pressure control. We've touched upon a little bit of charge pump. More on that in a moment. Heat is a big issue, and we've already mentioned that. Sometimes if we go and do some work at a pulp mill, the maintenance superintendent will say, hey, hope you guys are going to cover some training on hot loops. That's another alternate description maybe for what they are thinking of as their hydrostatic drive. They're calling it a hot loop. Is it true that hydrostatic drives tend to run warmer than many open loop systems? Yeah, that's absolutely true, and it makes sense when you see that the fluid from the motor is constantly returning back to the pump, or at least most of it is. So this is a good time for us to think about that hot oil shuttle that Jeff was mentioning, and that is to see that pressure on the top line, that dashed pilot line. That's not a flow line, that dashed line coming down to the hot oil shuttle. That's just a pressure line, and it bumps our hot oil shuttle down based on the high pressure side. And then let's follow oil leaving the motor some of that oil leaving the motor, or perhaps more correctly, we could say thanks to the charge pump that is pushing fluid into the return side. Okay, which exact oil molecules are moving through the hot oil shuttle, the ones returning from the motor or the ones added by the charge pump? Doesn't matter for this point in our discussion, but notice that flow is leaving from the return side of our hydrostatic loop and is moving through another pressure valve, never set too high, okay, actually needs to be set a little bit lower than the charge pump relief, as mentioned earlier. Otherwise, we won't direct any fluid on this path. And so this is our opportunity to direct some oil back to tank, perhaps to get some contaminants out of the system. Otherwise, hydrostatic drives can tend to hang on to contaminants and have them circulate. And certainly an opportunity to get oil back to the tank. For cooling, perhaps oil will pass through a cooler on its way back to tank, or perhaps once the oil is in the tank, if temperature is being measured, perhaps there is an auxiliary cooling loop. Number of ways of looking at it. This particular example, the way we put it together, includes, I guess, what we would call a flushing loop, in that our hot oil shuttle flow is actually entering into one of the case ports on our pump, and even though schematically it's drawn as on top of the cymbal, in fact it would be entering the case from the bottom, and then our final case drain from the pump is shown going back to tank. And while schematically it's being depicted as on the bottom of the cymbal, as most of you know, that final case drain is going to leave from a port on the top of the pump case. So schematic symbols and the way things get ported and built in the end aren't always a perfect match, are they? Right? It's a depiction of general flows and connections, and we don't have any port labeling. This is just entirely a generic system for training purposes. If I move my controller for the swash plate back to neutral and then move it into reverse, now you've got exactly the opposite flow action taking place. And so oil is leaving the hydrostatic drive at 6 o'clock and moving over to our hydraulic motor and entering at 6 o'clock. Everything is happening in exactly the same way, just on the opposite side of the loop. If we move that load resistance to max, bam, there's that same action again with our pressure valve, but this time the cross-port relief is on the bottom of the loop, and so there has to be two of them, okay? Notice, of course, the check valves, which sometimes get referred to as makeup check valves. Other manufacturers refer to them as replenishment check valves. I think that's sort of a term from the UK that's popular. All of those terms make sense. It's oil from the charge pump being added to the return side of the loop so that there is fluid that can leave through the hot oil shuttle, and also to make up for oil that leaves the system on the case drain line of the motor, oil that leaves the case drain line of the pump, all of the losses, right? It's a closed loop system, and so all of the oil that leaves our main hydrostatic pump at 6 o'clock and eventually returns back into it, in this example at 12, all of that oil has to be maintained. If we're going to allow for oil to leave the pump or the motor due to flushing for lubricating and cleaning out, and for the clearance between the parts of the pump and the motor, if we're going to let case drain oil out, and if we're going to allow a hot oil shuttle assembly to be there, we've got to make sure we add an additional amount of flow for that amount of flow that leaves the hydrostatic system and actually goes back to an atmospheric tank. So said another way, all of the oil that returns to tank, perhaps on your charge pump relief, hot oil shuttle relief, your motor case drain, your pump case drain, if you added up all those flow rates together, that is the flow rate of your charge pump. It has to match, okay? Save for any volumetric efficiency issues that might happen at high pressure due to slippage inside the pump or pump wear. All right, I think there was a question that showed up there briefly about the size of the hot oil shuttle valve and the charge pump. And so I'm not sure where that question went, but let me just see if I can address that briefly. Read through your hydrostatic pump supplier's application notes on that. I was just reading one yesterday from Danfoss from their Series 90, recommending that you choose a pump whose charge pump element, because quite often you have options, will provide at least 10% of the flow of your entire hydrostatic loop. So a charge value from the fixed displacement charge pump pushing into the system as much as 10%, or sorry, minimally 10% of what you have as maximum flow around the entire hydrostatic loop, okay? And those numbers may vary a bit depending on which manufacturer of hydraulic motor you chose. They may also have some flushing needs, and that may come from the charge pump as well. So there's sometimes some room in there. We've worked with hydrostatic drives where the charge pump is sometimes, surprisingly, 30% of the entire hydrostatic drive system maximum flow. That's a very large charge pump scenario. But mostly we run into that scenario where the hydrostatic drive is going to be operated on mobile equipment, usually the oil field, in some very hot climates, and there's concern there. All right, let's see here what other questions I might be able to answer. Case strain oil returning directly to the tank without a filter. Isn't it harmful for the system in some circuits? Wow, yeah, so that's a really tricky discussion to have there, Dharmalingam. I'm not sure exactly how to give one answer for that. But yeah, hydrostatic drives can be very tricky to look after if there is going to be particle contamination. Probably some of the toughest to maintain systems that we bump into from the point of view of filtration and particle cleanliness comes in the oil field, where the coiled tubing units, they unplug the injector, which is the motor half, from the pump. They uncouple it, quick couplers, and then they plug them back in when they're getting ready to do a service job, and it's a great time to introduce contaminants as those quick couplers come together, and now perhaps you got quick couplers stuck in the hydrostatic loop. So in machines like that, you will generally find very large elements so that the pressure drop through the filter isn't too great, but very large elements that are filter elements that are filtering one direction at a time. So two sets of filters, one on the A and one on the B loop. Otherwise, a lot of case drain flows as they go back to tank should not be filtered lest you get in the way and cause some back pressuring with that filtration that could cause damage to the pump or the motor. But then you may choose to have one of the most effective filtration systems out there, which is called a kidney loop, drawing oil from the tank on a special gear pump usually whose only job is to do filtration perhaps and cooling, and to circulate oil from the tank through a cooler and a filter and then right back into the tank and get some assistance with fluid cleanliness in that manner. What is the maximum, Pradeep says, what is the maximum allowable operating temperature of a loop for oil in a VG68? I'm not sure. We'd have to look in the manufacturer's technical specifications. But generally speaking, hydrostatic drives can come up to 70 degrees C, perhaps 80 degrees C, 180F. That is about it. They become very hard to look after and keep the oil in good shape and keep seals in good shape at anything higher than that temperature. And so then one does have to work at making sure cooling is taking place. Jonathan was asking, what is the directional control valve for? Yeah, so if I go back to our simulation here and you're seeing that 3-port, 3-position here, I'm just going to reverse directions again. That 3-port, 3-position directional valve there, that is the hot oil shuttle. It is bumped into position, piloted into position by the high pressure side, and flow is exiting from the low pressure side. And that is the valve that is just there to select. That's all it is. It shuttles to select the low pressure side of the hydrostatic drive loop and allow oil from that low pressure side to be connected to the hot oil shuttle and allow a flow of oil to go back to tank for flushing, cooling, filtration. Yeah, I hope that's the directional valve that you were referring to there, Jonathan. All right. Sorry if I'm not keeping up with all of your questions here. I'll answer maybe one or two more. When we are using, Arnab says, when we are using a hydrostatic drive in mobile equipment, and so you ran into a scenario where you had to tow the machine. Yes, some hydrostatic drives have a towing valve. So thanks for reminding me about that. I will point that out, that it's pretty important if you have a propel machine that broke down and now you need to winch that machine up onto, say, a deck truck to take it away somewhere or tow it a short distance. Oh, it can be very tricky. You've got to allow for the flow to pass through the hydraulic motor. And so some pumps include a bypass or a towing valve. Actually, ours does. Here, I'll just briefly jump over to a look at our hydrostatic system. This is a pump that I'm going to be running here shortly. This is the hydrostatic drive in our shop. It's just a wee baby that does 7.4 cc's per revolution at maximum on the main piston rotating group. We've got a gear-based charge pump happening there. But this lever here, this is the tow bypass. If I push down on that lever, A and B ports are directly connected together. And so if the machine is broken down but the pump is still connected to a hydraulic motor, the hydraulic motor could turn and circulate oil through a bypass valve here at the broken down, engine and pump end. If that's what happened, the machine broke down, and that in turn will not try to turn the rotating group, the cylinder barrel, which will then not try to turn the prime mover and cause all kinds of resistance and damage and bad things. So that's a bypass option right there. I better put it back up into normal, otherwise I might forget later when we run that. On our training system here, here's our main A port outlet and our B port line as well that move over to our motor, but we also added a needle valve to give us some very fine control to allow flow to take place, and that allows us to do some work with a hydrostatic drive even with our hoses uncoupled and actually come on stroke. So yeah, the tow valve can be an important element, most certainly. I hope that's what it was. Okay, and Jeff is asking some questions about filtration. Where's the best place to put them on a closed loop system? In line, yeah, so on those hydrostatic drives, Jeff, that I was telling you about for coiled tubing injectors in the oil field where they put one on each side, generally they've got those located fairly close to the pump side of the hydrostatic loop. And they've generally got that filtration happening as oil leaves the pump and heads towards the hydraulic motor. Oil on the return side bypasses the filter with a bypass check valve that's typically in that type of loop. All right, Brock Godfrey, hey, from Australia, welcome. Good to hear from you, sir. Good morning, Carl, he says. Love to hear your thoughts on... Yeah, it's morning for me. What time is it for you? My goodness, must be late there. Love to hear some thoughts on performing volumetric pump testing on closed loop pumps, particularly in the field, as in still in the machine. Yeah, well, wow, that can be a little tricky to do, can't it? Especially since if you have a hydrostatic drive that is turning in both directions, since you have so much swash plate control devices typically on a commercial grade pump. We haven't volumetric tested hydrostatic drives in the field per se. We test a lot of open loop pumps for volumetric in the field. I don't see any reason why you can't do it, but it's much more complicated procedure, isn't it? Especially since you're going to have flow in both directions, and if you're going to be using flow turbines and instruments to help you, can get very involved in making sure that that you can have flow in both directions, that you can measure flow in both directions. I think an awful lot of high-end hydrostatic pumps, if there are needs for that, probably end up in a hydraulic shop in bench testing in a lot of cases. But theoretically, I can't imagine a reason why it couldn't be done, but quite an involved procedure for sure. Samer says, in the case when the pump is in neutral, okay, and the maximum pressure in the circuit will be 300 psi. Okay, I think I'm following so far. If motor has a load on the shaft, can that load run away and make the motor work as a pump? Yeah, I mean, if the load on the shaft is like, say, a winch and gravity could pull it down, absolutely, absolutely. And so a lot of pump manufacturers, when they talk about some of their setup procedures, they want you to remember at neutral that that your driven load, the motor may not be locked, and that you need to take some steps to lock that motor. So a lot of drive motors for an excavator and different types of machines, as you know, will have that spring-applied hydraulically released brake, so that when you come down to neutral and you're below, you mentioned 300 psi, so I'll pick a number. If you're below 450 psi in the drive loop, perhaps some sequence valves will make sure that that spring-applied fail-safe brake at the hydraulic motor will lock on. We've got that on our motor unit here. Okay, we've got a motor unit here where the brake releases automatically. The brake releases automatically. I think it's about 100 psi on ours, and the brake will release. Here's a depiction of our brake shoe against a wet disc pack that's inside our motor. This is just the manufacturer's exact symbol for this particular Eaton JMV that we put on here. And so that releases automatically. And so when you come down to the lower pressures, the counterbalance valve closes, and the brake is vented, and the spring applies it. And so there's a combination of things happening between the counterbalance valve and our brake release to set our motor free. Because yeah, otherwise we've got this 250 pounds worth of blocks, steel blocks, but they're only loaded onto half our chain. And yeah, we can stop the load halfway down, and gravity doesn't interfere due to the spring-applied hydraulically released brake that locks on as our counterbalance valve comes to the center or neutral position. All right, there you got a little spin around view. Okay, let's see where we're at here time-wise. Time is flying quickly, I think. Just going to go through my notes quickly here and see what topics we were covering. So, overheating with cross-port relief valves on the more industrial-grade hydraulic pumps is dealt with during the pressure conditions by adding a feature that we might call pressure compensate. So if you're playing along, go ahead and hit that button that says Compensator. And what that did, wow, what did that do? That added a lot of stuff. So what I think you'll notice is that our two cross-port relief valves have moved to the inside. I'm going to circle them here with my mouse arrow. Perhaps you'll see what I'm circling in the middle of our pressure control branch, that our two cross-port reliefs move to an inside position, and they're just there now for shock. Those relief valves are generally 3, even 500 psi higher than the trigger point for what we're going to call sequence valves. The sequence valves look very much like pressure relief valves, don't they? Except that generally sequence valves are being used where the outlet of the pressure valve is not on its way back to a low pressure or atmospheric vented tank. So these sequence valves are up to something else here. They're now going to be used to do a different effect. So again, put your hydrostatic drive in forward. Oh, I had my load resistance all the way. Put your hydrostatic drive, say, halfway forward, and then let's slowly overload the motor and see what happens. So what you'll notice is that the sequence valve on top is popping open shut. That popping open is sending fluid through a special passage inside the pump to, yes, now we also have to add a servo piston. The very same servo piston that moves the swash plate into position for the speed of flow, for the rate of flow and motor speed that you wanted. That very same servo piston is now being used as part of the maximum pressure control scheme, where instead of venting or cross-port flowing the entire flow rate of the pump through a spring-loaded poppet, which will just cause a lot of heating, it's now instead pressuring the opposite side of our servo piston and taking our pump to the neutral position. Now, as soon as the pump reaches its perfect zero swash plate position, and keep in mind, our operator control lever, or the control system, if it's an industrial plant, was still asking for forward flow. So that flow request was still there. But now that we're off stroke temporarily with the sequence valve popping open and pushing flow, or pushing a pressure value, it's not so much flow, pushing a pressure value to that servo piston, our pump swash plate, when it reaches zero, is essentially not pushing any fluid, and of course internal clearances in the system will take that pressure down a short way, and as soon as that pressure drops a little bit, the spring in the sequence valve will slam that sequence valve closed once again. The pump will attempt to come back on stroke because the command signal is still there. But perhaps the pump will only make a half a degree or a degree of angle on the swash plate before the pressure builds up, because our obstruction to the motor shaft, our overload to the motor shaft is still there, and so the pump just goes back off stroke again. So it's literally hunting on the tiniest amount to sort of keep us at a standby pressure that is the maximum of the system until someone takes that obstruction away. So that is what it means to add pressure compensate, and of course the value. Oh yes, the value to that feature is what? The value to that feature is that we get rid of a terrible heating problem, and so if there are going to be some significantly long moments where we're going to be in motor overload condition, this is the more energy efficient way to handle it from the prime mover, diesel fuel electricity, and then that's diesel fuel or electricity that you didn't buy simply for the purpose of overheating your hydraulic fluid. So it's an energy saver all around. Might be good for me to point out once again, if we were to go back to simple ideas, that when we put the controller back in neutral, watch that bottom gauge on the return side of our hydrostatic loop. Watch that value, 260 psi, and we sort of detent in there, ka-chunk, in the center position, and we find out the pressure comes up to 300. Well, that makes sense, doesn't it? With the same pressure on either side of the loop, our hot oil shuttle went to the center position, blocking access to the 260 psi hot oil shuttle. So now we are completely reliant on the charge pump's relief valve inside the pump. We better have that charge pump relief valve in there, or that little shaft in the middle will snap in half. It's always a fixed displacement pump. So that explains why our charge pressure gauge here at the top and all of our loop pressures are now sitting at 300. Those three should be equal when the pump is in neutral and the neutral or the centering adjustment is correct. More on that in a few minutes. Yeah, let's have a look at maybe some of these common features that we're talking about here as they show up in other common manufacturers' models. You may not have access to all of these today, but Rexroth A4VG was mentioned. And again, this is just a very generic depiction for general learning only. Please work with the manufacturer or with your hydraulic system integrator if you're going to make any adjustments to sometimes the good handful of adjustments or more that are available on the outside of the case of these pumps. What we're covering here won't be enough to help you do that safely and correctly. But here we are bringing the pump on stroke by means of, well, we've got it set up there that we're working with a manual controller. So sometimes you actually have linkage involved. We could move over to an electronic controller, but really the valve, the servo valve, doesn't look much different. It's just that now we've got solenoids that are being operated by variable current in pulse width, or we could run from a hydraulic pilot, and then you see those ports Y1 and Y2 that need to be connected to an external pilot controller of some sort. Here's one on our stand that you could have a look at. This is a pilot controller here, and yeah, we could have taken the pilot controller ports and connected those to A and B, and then we would pilot our pump with hydraulic pressure instead of with the electrohydraulic solenoid valves that are there. So that's another option. There's usually a number of ways of piloting that servo piston. But in the example of A4VG, you see the high pressure relief valves in the middle here. Just get some color on that top line there, some pressure color going. So those are your cross-port relief valves. They are generally set anywhere from 300 to 500 psi higher than whatever pressure valve is bringing you that pressure compensate feature. And that in the Rexroth pump is over here, pressure cutoff. And so look at the symbols that you've got if you have this model of pump. There'll be a little shuttle valve. Okay, this is not the hot oil shuttle, not at all. It's just there to select the higher pressure of whichever side of the loop, hydrostatic loop, is doing the hard work. And then if we overload, let's overload, that'll pop our pressure cutoff. And this time what's happening is instead of pressuring the opposite side of the servo piston with full servo pressure, it bleeds it off and lets the springs inside the servo piston return the pump to its neutral position. So very similar scenario. You'll see the hot oil shuttle there. Yeah, all of the regular features hard at work. Let's have a look at servo action from a Parker Gold Cup pump for a moment. You may recognize this diagram as a famous cutaway diagram from one of their technical publications. And we added a few things and brought it to life. And of course, what you'll notice is that we can't show you the cylinder barrel spinning in 2D. So you're seeing some pistons there. You know, you'd see maybe 4 of them if you were to cut away of the 7, maybe. But we can't show them spinning in this view very well. So imagine that the cylinder barrel is still spinning, but pump control is handled by a bit of a different mechanism, a bit of a crescent-shaped chamber that is sealed up with a vane type of construct. And then there's a little item called a servo arm in the middle. And how that servo arm is moved is a topic for another day. But there, again, is the same type of scenario for moving the swash plate into position to produce flow either A port to B or B port to A. And again, if we were to load up the pump, there are a number of valves. We're showing them sort of in the cutaway style, the way Parker did for the Gold Cup cutaways. Some people call that the brain box at the back of that pump with all those slip-in cartridges hard at work. And so there is that high-pressure sequence valve that is triggered and has sent oil down what we call the pressure override tube and into the opposite side of the vane chamber there to bring the swash plate back to an off-stroke or a centered position, even though the servo arm is still in the position that the operator wanted it. It's a little bit involved for us to explain that, but I'll come away from maximum resistance at the hydraulic motor, and we'll see that the pump comes back on stroke. But still, cross-port relief valves, they're just referred to as a dual-level relief valve in this pump, and they just pop open. They just for a very brief time, if the pressure spike is more than 500 psi higher than the setting of the high-pressure sequence valves that trigger that compensate action. Okay, oh my, there's so many things we could cover, and we won't have a lot more time. But just to move over to Danfoss Series 90 as another very good example from out there in industry. Maybe I'll put the hydraulic piloting on so that you can see an example of the external pilot controller that I showed you briefly on our stand, which just pushes on the main control valve that's bolted to the side of the pump. Otherwise, you see all the same features. Oh, tow valve, right. The towing valve was mentioned earlier. The multifunction valves in the Danfoss 90 come with a wrench setting that you can release on what is otherwise the cross-port relief valve. You have to check their manual to know which wrench flat you're turning and jam nut, but here it is. Here's that butterfly shape. That basically lets you open up and create a complete cross-flow path so that if you have to tow your propelled machine, say, a distance because it broke down, your motor could spin freely and circulate oil through the towing valve component of those multifunction valves and allow you to rescue your machine if it broke down. So those are some really typical scenarios there. Well, let's see. Let's go back to some questions there. What are major factors for increasing the life of pumps for a hydraulic system? Sundarapalli, that's a great question. You know, keeping temperatures under control is key, so keeping track of that. Making sure that the fluid levels are topped up is important. Making sure that solid particle contaminants do not get into the system. Making sure that water does not get into the system. Making sure that pressures are checked from time to time to make sure that maximum pressures are still set correctly. These are major factors that if the pump gets regular checkups in that way and shaft to prime mover alignment is maintained, all of those critical mechanical aspects can quite often make a good quality hydraulic pump last many decades if it gets that kind of tender loving care. Great question. Pradeep is asking, how long, let's see, how long can a hydrostatic run in neutral condition? Oh yeah, pump in neutral and cooling but not working the loop. Yeah, if everything is set correctly and the system is well designed, endlessly is a fair enough answer. I mean, it's an unnecessary consumption of energy on the part of the prime mover, but there's no reason why, if it's designed well and has the correct elements to it, the pump is meant to spend enormous amounts of time in neutral if need be. Yeah. Sammy, Mr. Sammy, he is asking, is there a relationship between the displacement of the charge pump and the main pump? Yeah, we mentioned that a little bit earlier on, just briefly, but you know, a lot of manufacturers of the hydrostatic drive will give some guidelines for a minimum amount of charge pump displacement. And as I was mentioning, I was reading through Danfoss application notes a few nights ago just to refresh my mind on some of those things, and they clearly stated in their literature to make sure that the charge pump displacement was at least 10% of the maximum flow rate moving around the loop. And so that at least type of statement is there to allow you to access fluid for flushing, cooling, and maintaining charge under all the scenarios that might happen for that pump across its full range of pressures and its full range of displacement. All right. Mr. Sammy is also asking, if I have to readjust a hydrostatic transmission, how do I proceed? So there's a bunch of adjustments, and one of the ones that is perhaps of great interest to many technicians when they run into this one is an adjustment that allows you to maintain neutral, whereby if these springs that are in that servo control piston, perhaps one of them changes its temper usually due to many overheating cycles that were much too high, or some other contaminant gets in there and is causing some sticking of that servo control cylinder, and you're going to have to, I mean, if you have sticking, it probably needs mechanical repair. But if you get into a scenario whereby when the hydrostatic drive is in the neutral position, so let me go back to our really basic teaching loop here. My mistake there, picked the wrong one. And let's go back to that very basic loop. Those three gauges, A side pressure, B side pressure, and charge, should all be the same when your hydrostatic drive is in neutral. And if they're not, if say the A side pressure is 340 and the B side and the charge pressure at 300 or less, that's an indication that that stroking piston doesn't want to sit in its perfect center position. Here, let me add the stroking piston here so we see it. And so you may need to make an adjustment that allows that servo piston to shift over just a tiny little bit. Let's do that procedure now, but please, again, keep in mind, this is just a procedure for our own pump here in the shop. We've practiced this. We've consulted with the manufacturer to make sure we're doing it right. Before you make that adjustment, work with someone who's done it before. Consult all your pump factory notes and an expert who knows your particular model of pump if you've never done this before. So I'm just going to uncouple my hydrostatic drive from the motor, from the pump. So I literally have a system that is blinded out. There's nothing wrong with that. That's just starting up in neutral. And I'm going to switch to my very basic pressure gauges. Our pressure values are going to read on an HMI screen. So we're going to see port A pressure. We'll look at port B pressure and see if it's equal with our charge pressure when we're running. And so we fired up. We'll just give it a moment to sort of come to an ambient state. And port A pressure and port B pressure are pretty close to 298 each. Charge pressure is 297. Oh, looks like our port B pressure is turning out to be just a few psi higher than port A and charge. It looks like port A and charge are the same. Well, let's do some work with this. So on our particular system, this requires the use of a hex key, and I like to check and see exactly where I started. I'm at about the 1130 position. Keep track of that. I've got to back off a jam nut. This is in the similar position on some other types of pumps as well. And if I was to move over, say, to this 1 o'clock or 2 o'clock position, look what's happening here. I have put a uncomfortable bias on the spring for our servo piston. In our port B side, it's actually attempting to come on stroke because of the way we've unbalanced the servo piston spring. Port A, port B pressure, those should be the same because I have not asked for any flow. I have not operated the joystick, or my process controller hasn't asked for flow in either the A port or the B port direction, and yet my pump is attempting to provide a B port flow and pressure. So my pump is now not in what manufacturers would call a good nulling state. They would call it a neutral point. They'd call it a centering point in some manuals. I can't think. Everything in hydraulics seems to have three names out there in industry. But let's reset. Let's reset ours. Let's get things back to normal. And so I'm going to watch the gauges, and it's not very far that I have to turn to get things back to normal. Right? I'm just going to turn my Allen key and see if I can get port A pressure, port B pressure, and charge pressure all to be exactly the same. Of course, we're in a learning situation here in our lab, so we've got things well controlled. Make sure that you understand how to have your machinery in a safe condition for this. Work with a technician who knows your model of pump very well the first time this adjustment is made on your machine. Might even be the factory that you wish to speak to, and I've got my jam nut locked, and I'm back into a good neutral state. I hope that's helpful. Let's see, we're 10 minutes after the hour, so we'll start winding down. And let's see, could you elaborate on aeration detection in a hydraulic circuit? Well, in a hydraulic circuit in general, I mean, quite often a gurgling noise and a lot of foam in the tank is an indication that you've got aeration. Cavitation also makes an interesting noise, but will not produce a layer of foam in the tank as the fluid returns. That's probably all I have to say about that one at this time. Peter's asking, how do you troubleshoot to determine whether an unbalanced servo piston is either by hydraulic fault or mechanical in a hydrostatic pump? When the servo control is left in neutral. Wow, yeah, Peter, that's a really good question. I would attempt to do the nulling or neutral setting that I just did and then spend a lot of time observing that machine in both directions to see if it stays at that null setting. If it turns out that after cycling drive, forward, reverse, back to neutral, it moves out of null again, having just made that adjustment, that might be an indication that there's something mechanically sticking, some contaminants in there. If you couldn't achieve nulling and get it locked in and see things return to normal right after, that would likely be a good indication there. All right, so what did we have left to cover? Well, perhaps we won't have time for too much more than that today. Just a point to make, though, as I mentioned hot oil shuttles earlier, coming across some good quality new mobile machines even where the hot oil shuttle is absent from the design. And if you do some research about developments in closed-loop hydrostatics on the web, you'll run into a number of papers, research, some of them done around the 2010, 2011, 2012 range, some of them done more recently around 2018. One of the ones I was reading called Optimization of the Efficiency of Hydrostatic Drives by by researchers at the University College in West Flanders, Belgium. The researchers were Van Wallingham, Dowsey, Pinton, Van Severen. They did a great paper to explain how if you have good software in an electronic controller that is monitoring pressure transmitters, that is monitoring all of the shaft speeds in the system, including the shaft speed of the prime mover, the diesel engine in the case they were explaining for mobile equipment, that if all of those points are well monitored, and if that same software and electronic controller are controlling the engine throttle, which is the use of energy, input energy, the burn rate of diesel fuel, and that same controller is in charge of piloting the swash plate of the pump, and, we didn't have time for that, also piloting the swash plate. We can actually pilot the swash plate in our hydraulic motor as well. This one is 2-speed, so we can change the displacement of the motor to 2 speeds, but many motors out there let you have infinite pilot adjustment between, and so that gives you many points of control. And what happens under that scenario is that the controller can optimize and find a best operating point. I believe one of the manufacturers, best point control, Danfoss likes to call it, their solution. Rexroth also has one through their software and controller. And generally, the principles at work, my good friend Simon at Danfoss was chatting with me about that, is to try and achieve everything that you need to drive the machine, propel the machine at the speeds you need, at the pressures you need, but keep the engine RPMs, keep the throttling of the engine down low, and improvements from 10 up to 25% energy efficiency are possible with that kind of very careful control. So lots of good things can be done with closed-loop hydrostatic drives to achieve good powerful control, good variable speed, and also a great level of efficiency. On lunchbox sessions, we've got a lesson laid out that you can subscribe and make use of that takes you through all the pros and cons and general concepts of control for hydrostatic loops. So that's a resource available through lunchbox sessions, and those are good things to get into there. Lots of new material constantly coming as well. The answer to our pop quiz question is coming up, but first I'd like to thank our partner Fluid Power World this morning, and remind you also that our next YouTube Live is on July 22nd. Mark your calendar. Counterbalance valves, motion control valves, pilot operated check valves. We'll do things in simulation mode. We'll do things that are live. I thank you, our participants, for joining us today. The services of CD Industrial Group, the YouTube Live this morning, and all of the simulations and the system of lunchbox sessions are brought to you by Nathan, Crystal, Robin, Chris, Ivan, Alex, Keelan, Mark, Lenore, and Owen. And we're sure glad that you could join us. Apologies if we didn't get to answer every question that came this morning. Welcoming your comments. If you have some yet, feel free to chat them through. So the pop quiz question when we started out was, can hydraulic cylinders also end up being used in a hydrostatic pump scenario? And we had one person, I'm sorry, I should have written down your name, but one person who commented very early on in the broadcast said, yes, hydrostatic drives can be used with hydraulic cylinders, and that is absolutely true. One of the most common ones out there, but certainly not the only one. We also run into pulp mill stokers that are running hydrostatic loops, running cylinders back and forth. We run into pulp mill bale presses that are running cylinders or a stamp, a ram in hydrostatic mode. And concrete pumps, if you know what those machinery do, here is a really great example from one of our live schematics of how a closed loop hydrostatic drive can be worked with a hydraulic cylinder. I want to once again thank you for joining us with our YouTube Live here this morning. It was great to see you all again. If you've joined us from having been with us last summer, that was great. And looking forward to seeing you guys very soon. Stay safe out there. I hope your machinery work is going really well. We'll see you again on July 22nd. Thanks for joining us. Bye-bye.